everyone, Daniel and I worked on the robotic soccer goalie. We evaluated learning and physics-based controllers for dynamic tasks. Goalkeeping in soccer is a highly dynamic sport, requiring a high reaction speed, accurate ball tracking, and predictive abilities. In our work, we replicated these challenging conditions in a robotic environment. Controllers designed for precision and speed operate to maximize exactness of the robot's movements. The industry standard for precise and fast controllers in factory robots remains centered around position or impedance-based controllers. These controllers exhibit rigidity, failing to adapt to minor environmental changes. Learning-based controllers prioritizing adaptability utilize diverse decision-making with generalized approaches. However, such adaptability often compromises precision, rendering these controllers less suitable for tasks necessitating exact movements.
To evaluate each controller, we created a soccer environment within Drake. Each simulated episode begins with 3 attackers, colored red, positioned 17 to 20 meters from the goal. They advance towards the goal, dribbling and passing the ball. When they reach a distance between 8 and 13 meters from the goal, an impulse is applied, propelling the ball at speeds between 44 and 71 miles per hour. We apply additional forces to simulate the effect of a player adding spin to the ball, forcing a curvature in the ball's path. The defenders, colored blue, are positioned 6 to 8 meters from the goal and act as visual obstacles, obstructing Spot's view without making contact with the ball. Spot attempts to block the ball while limited to the goal zone, which is within the goal's width and 3 meters in front of it. Spot's controllers begins with RGBD information, which is gained from a camera in Spot's hand. 2 white points from the RGB image are used for mobile segment anything, a lightweight version of meta segment anything model. From the segmented image, the ball center is estimated. By combining data from the depth camera and Spot's internal pose estimations, we use the pinhole camera model to predict the ball's position in the real world. Given this information, the predictive controller, utilizing the history of the ball's locations, identifies a target for Spot to move its hand to block the ball. If the target is within Spot's operational range, a diff-IK controller commands the joints to move to this target. If not, Spot goes into tracking mode, where it aligns itself laterally with the position of the ball based on its calculations. We tested 5 controllers. For baseline evaluation, we used a controller that would block a random target and one that would track the ball laterally. We test 2 physics-based controllers, one which uses 2 points to predict the ball's trajectory, and another that uses 3 points to sample between additional spin forces that affect the trajectory of the ball. The trajectory is then used to predict the target. The ODE LSTM is given the last 3 ball locations and times. The neural net estimates the velocities of the ball at that last time point. The best blocking position is calculated by integrating from the last known point to 0.5 seconds in the future. Finally, the GRU and RNN are given the last 3 ball locations, and the neural net predicts the optimal blocking position.
Here's an example of a shooting scenario. Overall, the sampling controller exhibited significantly better performance, achieving a block rate of 36% compared to all other controllers. The ODE controller was on par with other physics-based controllers, attaining a block rate of 28%, which was better than the pure physics controller with a block rate of 24%. This suggests that integrating physics principles enhances the predictive accuracy and effectiveness of the controllers in dynamical systems. The neural network-based approaches were unable to outperform the baseline controller in tracking tasks. This outcome suggests that the neural network models, particularly the RNN, may have struggled with the complexity and unpredictability inherent in the tracking task compared to more specialized or simple controllers. While the sampling-based method proved superior, the performance of the ODE suggests that it could be an effective controller for dynamical situations where the physics of the environment is not well understood. Our findings are promising in guiding controller selection for dynamic tasks that require high degrees of accuracy, such as in search and rescue operations. This research advocates for the development of more dynamic and adaptable robots. The limitations of the study are that all controller evaluations were assessed in simulation only. Game simplifications, such as the ball being allowed to pass through defensive players during shooting, do not reflect real-world scenarios. In future research, we aim to delve deeper into continuous neural networks for estimating dynamics across various time samplings, with a particular focus on liquid time constant networks. We also plan to explore the potential of combined methodologies. Additionally, we intend to conduct evaluations of the controller results, comparing their performance in both simulated and real-world settings. Thank you!